Okay, yeah, thanks for the invitation. It's really a lovely conference. So yeah, so this will be based on a paper I posted in September, and then a new paper which maybe should appear this or next week. And then there's also a very closely related paper by by Jonah and Edward. So yeah, foundation of our holographic dictionary is this relation between the boundary partition function and the gravity partition function. So you consider, say, the CFT on some compact Euclidean manifold, and then that's supposed to be equal to the partition function on the gravity side with M as the supply the boundary condition for the gravity. And so on the boundary side, there's a parameter called n, which characterizes number of degrees freedom, then related to the g Newton by 1 over g Newton. Yeah, so here, just for simplicity, I just write it equal. So of course, it's normally not possible to calculate this gravitational partition function in the, say, in quantum gravity regime. So what we mostly have been doing is to look at the large n limit. Then it's related to the g Newton goes to 0 limit. And so, so this has been used everywhere since day one of ADS-CFT, and yeah, really underlies almost everything we know. And the limit on both sides should be understood really as a symptotic expansion. And in the respective parameters here in 1 over n, here is in g Newton rather than strict limits. Okay. So for example, the right-hand side, you should understand it as a trans series, say, which you expand in terms of the saddle point of the Euclidean path integral. So mi is the saddle point, and with the boundary given by m. Okay, so this I sums over, say, subdominant saddles. And so the reason this behavior appears is because in the gravitational path integral, g Newton only appears as the coupling constant, 1 over g Newton in the action. And so you just have this structure. So follow Edward, I will just call this a smooth behavior. Okay. So on the gravity side, we always have smooth behavior when you take g Newton goes to 0. And so, but not all is well with this relation. So one problem has been recognized early on is so-called factorization problem. And say if you look at the boundary, which consists of disjoint manifolds, say M1, M2, and then the boundary partition function should factorize by definition. But on the gravity side, then you should find the saddle point with M1 using M2 as your boundary, okay? But often on the gravity side, you have this kind of wormhole configuration. And so that means that the gravity expression do not factorize, okay, due to those wormholes. And so this problem, in a sense, it's, you can say, quote and unquote, solved in JT gravity, which you can show the gravitational path integral is really equal to ensemble averages on the CFT side. And then also there's no factorization. And also for pure ADS-3 gravity, there's also some indication that the maybe, yeah, which you can also, maybe some random CFTs on the left-hand side. Again, you have to do some kind of average. Okay. So these two series are special. It's because these two series, you can make sense just based on a Euclidean path integral. Okay. And that's not believed to be the case, say, for higher dimensions, or for series come from, for the duality come from the string series, say ADS3 times S3 times K3, etc. Okay. So now the key question is, what should be the story for higher dimension? Okay. And there's another problem with this equation, which is not normally much emphasized, okay, which I call erratic n problem. So this was, as far as I know, was first really mentioned in the paper by Edward in 2022. And then in this paper in September, I tried to emphasize it a little bit more. And so implicit in this equality, so we said on the gravity side, this expression exhibits so-called smooth behavior, okay? So implicit under this relation is that the boundary theory, when you take the Lorentzian limit, should also exhibit smooth behavior, which means that in the Lorentzian limit, the boundary theory should exhibit, again, this kind of symptotic expansion, summing over different Lorentzian saddles, say, in this kind of pattern. Okay. Yeah, by the way, there could be logarithm corrections which are suppressed here. Okay, you can easily include logarithm corrections in this kind of expansion. So what is different from CFT and the gravity in the corresponding limit is that in CFT, N not only provides a coupling, say in the Lorentzian limit, but also characterize the number of degrees freedom. Okay, so N actually come also as a rank of the matrix, for example, in the encode for Yang-Mills theory. So then this assumption, somehow we kind of always assume, okay, somehow take for granted, it's actually highly non-trivial. And probably not true. Okay, so actually I will provide some proposal that actually this, maybe there are places we can see that this is not true. Okay, so now we have two problems. And then now we can apply, say, Occam's razor. Maybe we can reduce the two problems into a single problem. And I want to convince you, actually, that's a good thing to do. Okay. So now let's imagine when you take the Lorentzian limit of the CFT partition function on some compact manifold, you not only have this smooth part, which we normally assume, but also have some kind of erratic dependence on N, which means that they don't fall into a trans series as this smooth part. Okay, you can define the rigorously mathematically, which I will not do it here. Okay, and so heuristically, this means when you go to N to N plus 1, things can be wildly different. Okay, order 1 difference. Anyway, so I also allow the situation that this erratic part can be exponentially small compared to the smooth part. Okay, so even in that case, we should still consider them. So in such case, then to match the CFT expression to the gravity one, the gravity one in the semiclassical limit just does not have such kind of piece. Then there must exist some kind of filter, okay, in order to compare CFT expression with the gravity expression. Means that there must exist some filter which takes your Lorentzian CFT partition function into some smooth behavior. And then we can equate to the gravity expression. Otherwise, the direct relation between the CFT and the gravity just does not make sense. Okay. The structure on two sides don't match. And this can potentially solve the factorization problem. Because now if you apply this filter to CFT on the disjoint manifold, and now because you have done this filtering to filter out this erratic part, and then the right-hand side does not have to factorize. Okay, so then that may provide a physical and a mathematical explanation for why somehow you have this non-factorization we see on the gravity side. And so, unfortunately, I will not give the explicit form of the filter, okay, other than just emphasizing its conceptual necessity. So new proposal, yeah, so this, say, for example, this filter could involve averaging N, and it could also involve some other kind of ensemble average. So right now, we don't know what is the right way to describe this filter, other than I just want to emphasize it must be there. And this can explain the long factorization problem. So now the proposal, so now let me just suppress the Lorentzian. You assume that this filter always involves the Lorentzian limit. So now the proposal is that take the CFT partition function, then you pass through this Lorentzian filter F, And then that would be the expression you identify with the gravity side in the semiclassical limit. Okay. And so we also should list conditions which should satisfy by this filter. And for example, when you act on the CFT partition function, you should get rid of the erratic part, only keep the smooth part. And also, if you act twice, if this is already smooth, you act on it, of course, you should not filter anything. So in a sense, this should behave like a projector. Okay, so project out this erratic part. And also, yeah, it's sensible to require this to be a linear. Say if A and B are some smooth dependence on N, means that they have ordinary asymptotic expansion, and then F should not worry about them. Okay, you can just take them out of the F. And also you require F to be real. Say they don't add additional phase when you do this filter. And also you require this to be positive. Say original positive things, when you go through the filter, it should be positive. Say to be compatible, for example, with unitarity. Okay. And so these are some basic conditions we can imagine that this should be satisfied by this filter. Okay. And in particular, these conditions will ensure that the filter will not spoil any current success imagined between the bulk and the boundary quantities. So currently, there are already tremendous success. Imagine many CFT quantities under the gravity side, say all these sphere partition functions, supersymmetric index, etc. Okay, so we should not destroy that. Okay, so now we will try to give an interpretation of wormholes based on this, this picture. So now let's just imagine at finite n, you consider CFT on this disjoint manifold. Then, of course, they factorize. Okay, so this is D1, just the partition function M1. And then if you apply the filter to Z1, and then you get the gravity partition function with boundary M1. Okay, so this is a single boundary. And now if you apply the F on the Z1 times Z2, then this should be identified with gravity side with boundary, disjoint boundaries M1 and M2. So now using the properties of F I showed in the last slide, so if I define the isolate the erratic part of the Z1, say the partition function or the Z2, which I subtract the filtered part, and then of course the filter on this erratic part should be 0. But the product, okay, of the erratic part of Z1 and the Z2, when you multiply them together, go through the filter, that does not have to be 0. Okay. In fact, if you plug in this expression into this expression, and then you just conclude that this part just equal to the wormhole part of the gravitational partition function. Okay, so if I use a slightly abuse of language, call this to be correlations among the erratic independence. For example, if these have some phase and these have some phase, then the phase can cancel, and then they may have a well-defined filter. Okay, so let's call this correlations around the erratic independence, and then the slogan is that then these correlations among the erratic independence actually are captured by wormholes. And you can trivially generalize this relation then to more than one boundaries. For example, you can consider connected correlations among 3 erratic part of the erratic partition functions, and then that may be described by this kind of wormhole on the gravity side. Okay. So on the Lorentzian side, the story is even richer. So again, let's first just try to review the conventional wisdom. So normally in the Lorentzian signature, we imagine we have a, say, sequence of states which depend on n. And then we imagine the sequence of states, say, somehow have some kind of Lorentzian limit, which can be described in the bulk by some Lorentzian manifold, say M. And then the observables in this state, in the Lorentzian limit, and when you take n go to infinity, and then can be related to semiclassical gravity quantities. So there are additional complications in the Lorentzian signature It's because on the for the Euclidean partition function, we are guaranteed. Okay, there's a Euclidean partition function for each n. Okay, so that's just by definition exists. But in the Lorentzian side, it's actually not obvious how you identify this thing for each n. Okay, so there's no canonical mapping of CFT Hilbert space at different n. So it's not for general state. It's not clear how you define this sequence and then how to define this sequence. Okay, and assume you can do that, then still on this side it's possible you may have erratic independence, but we know the right-hand side does not. Okay, and then again we need some kind of filter. Okay, so the precise rule for the Lorentzian signature is not quite clear, but we have a very powerful tool as our friend, which is analytic cantillation. Okay, so from Euclidean analytic cantillation, we can actually try to get some feeling what this kind of filter does on the for the Lorentzian signature. So we argue, in this case, the erratic large n behavior of the boundary CFT actually are related to the emergence of the closed universe and the black hole interiors. Yeah, it just CFT Hilbert space depend on n. Yeah, take an equal to super Yang-Mills series at the different. Yeah, SU2 and SU3, there's no canonical mapping between them. Yeah, that would be a subset of state. Yeah, for subset of state you can do, but not full Hilbert space. Good. So far, what I said seems, yeah, of course, people are worried about this wormhole story, this factorization story a lot. Okay, the huge amount of literature. So far, what I've described may sound to you just like some kind of rebranding. Okay, but I want to convince you in this talk that actually there's new insights one can learn from here. Actually, based on this, we can make some predictions, which can be checked explicitly, say from CFT calculations. Okay, so the plan of the talk is first I will mention some predictions we can make on the erratic independence on the Euclidean partition function. And then I will describe how close universe come from this erratic independence and the black hole interior. Okay. Yeah, but this is a little bit wildly ambitious plan. So if I can go through one of them, that's already be very good. So under our proposal, that if a Euclidean manifold M can never appear as a boundary in any wormhole saddle, okay, just say, then that means that any this kind of correlation under this filter must be 0, okay, because it cannot appear as a boundary in any wormhole saddle. And then we will say, in this case, the CFT partition function actually only have smooth part. There's just no erratic part at all. Not even the exponentially small erratic part, okay? And just smooth part, period. Okay. And conversely, if there exists some wormhole saddles with M as a boundary, then that's an indication that the erratic part of M is non-zero. Okay, so I will just use this as criteria, okay? Then try to deduce what would be the erratic part of the CFT partition function. And then we can check it. Okay, so we can make predictions. Okay, so now let's try to look at the CFT at finite but some large n. So we can consider energy levels of order 1 independent of n. So below those energy levels, there's no erratic independence. Okay, we can really count them. But if you go to the black hole state of energy of order n square, then they will be highly erratic. Okay, highly erratic. So now let's look at the partition function. Okay, which sum over all states in this weighted sum. So now, then from a theorem, say of Witt and Yao in 1999, and also Tsai Galloway, then they show, so this thermal partition function is defined for manifold S1 times SD minus 1. Okay. And for that kind of manifold, their theorem show that can never be the boundary of any wormhole. Okay, then from what I just said earlier, then that means for thermal partition function, the erratic part of the in the Lorentzian limit is just identically 0, not even exponentially small part. Okay, just identically 0. And so I call this to be complete self-average. So remember, when you're above the Hawking page temperature, then here you actually sum over the black hole states dominates. Okay, but somehow the sum over black hole states, they complete self-average in this thermal partition function. And we can also, for more complicated observables, Euclidean observables, say more complicated partition functions or Euclidean correlation functions, then they will involve the OPE coefficients. Again, I will use this label A, always means the state of order n to the power 0, and I of order n squared. So then we can have OPE coefficients between those state of order 1, energy over the 1, then again, they're not erratic. You can define them in the Lorentzian limit. They have a well-defined Lorentzian limit. But now if you look at light, heavy, heavy, so one light operator, and the rest, the two ij are heavy, and we expect this to be generically erratic. Okay, but this quantity is important when you look at correlation functions of single trace operators. Say, for example, in thermal ensemble, etc., or vacuum correlation functions. And then again, from this Witt and Yau theorem, since when you insert this single trace operator, they should not back react to the geometry. If there's no wormhole for the thermal partition function, then there's no wormhole for this kind of Euclidean correlation function. Then that means, again, this kind of quantity, say the light, heavy OPE, and you sum over all the heavy states, when you do this kind of average, also complete self-average. Okay, you don't have any erratic independence at all. But now you can consider, say, heavy, light. Okay, one heavy state, two light, and again this will be erratic, and then you can find Euclidean wormholes to see actually this kind of quantity will still have some erratic part. Okay, so this is a prediction of our formalism, and so I call this to be incomplete self-average. And similarly, if you look at the heavy OPE, again, in general, they will be erratic, and the claim is that this kind of sum, okay, in general, will also contain erratic part, and again, this is incomplete self-average. So example, a simple example is a genus 2 partition function, CFT, for example, for two-dimensional CFT, which you can decompose in the channel written in terms of the OPE coefficient like this. And the claim is that this will involve smooth parts and erratic part depend on n. And in particular, this erratic part is reflected in these wormholes and connect to genus 2 manifold. And so here I want to make a claim. So as far as I have checked, okay, long on-shell Euclidean wormhole saddles can all be interpreted in terms of incomplete self-average of OPE coefficients. Okay, so this incomplete self-average will give rise to this kind of wormholes. Okay, will give rise to the erratic part in the partition function, and then will give rise to wormholes. And so I emphasize here they involve OPE coefficients and of heavy operators. So it's intuitive in this sum, somehow why this contain erratic part. It's because sum over AB is a discrete sum. Okay, you have small number of this order 1 number of this state of energy of order 1. And so if you have some erratic behavior, then this sum is not going to average over it. Good. So let me just mention that the statement actually applies both to the external wormholes, which connect, say, disjoint manifold, or internal wormholes, corresponding you add a handle. okay, to your previous, yeah, say to your otherwise connected manifold. And so again, this kind of internal wormholes can be understood as incomplete average of those erratic OPE coefficients, and then they when you go through the filter, and then they manifest themselves in through the these internal wormholes. And here, there's no average or random couplings in gravity effective field series needed in order to understand those internal wormholes. Okay, so just on the gravity side, it's just normal, and those kind of erratic behavior is in the CFT side. Okay. So there's also another type of wormholes. So for example, the double cone of Sard, Schenker, and Stanford, and this t square times interval of the Corson and Jensen, so those wormholes is a little bit different in nature. Okay, so the first one is more like a complex saddle for Lorentzian observable. Okay, so it's more like a complex Lorentzian saddle. And so this Corson and Jensen wormhole, it's not unshelled. It's a Euclidean it's a Euclidean wormhole, but it's not unshelled. But I also believe that maybe one way to understand this thing is actually by considering as actually a Lorentzian complex saddle. Okay, and anyway, so they describe somewhat different physics. Rather than OP coefficients, they probe the level statistics. Okay, so again, it's tempting to conjecture that those wormholes, they describe this kind of Lorentzian partition function, analytic continued partition function, and you go through the filter. Okay, you go through the filter. Okay, so now let's go to closed universe. So closed universe is with selective cosmology constant that can be obtained by analytic cantillation from reflection symmetric wormholes, which was long discussed. And so here we can consider two types of wormholes. Say if you have external wormholes, and then they connect M- to M+, and then you do analytic cantillation on this reflection axis, then you get the Big Crunch and Big Bang universe I call U. Okay, so this reflection slice, reflection symmetric slice is preserved under analytic cantillation. So now if you consider internal wormhole, okay, now let's imagine this one is actually also reflection symmetric, even though I didn't draw very well. So let's imagine this is reflection symmetric, and then you can do analytic cantillation, say with this treat as time, okay, along this slice. And then what you get, generically, you get ADS, which comes corresponding to this connected part, and entangled with a baby universe come from this handle part. And so you get two types of closed universe. Okay, so this is normally entangled with some asymptotic ADS. This is just closed universe. So now let's first look at this type of a closed universe. And so the standard path integral story is that if we consider the lower half of this Euclidean manifold, insert, say, single trace operators there, which I collectively denote the single trace configuration as capital X. And then you do the path integral, then that defines a state in the Fock space of this closed universe. Okay, again on this slice. And then the full path integral, both insertion in the past and in the future, then gives you the overlap of this such state. So by the way, this should be an over complete basis of the Fock space. And so this overlap, say, also include the correlation functions, say, of the Bach operators and etc. Okay. And now we connect this Euclidean wormhole, okay, now with the correlations with the erratic part of the CFT partition function, but now with some kind of single trace operator insertions. Okay, so you have your original partition function, but now with the single trace insertions, and you look at erratic parts. And now this wormhole amplitude that's related to this correlation. And now we have, and if you just equality, then we have relates, okay, the Hilbert space of the this closed universe with just correlations, okay, of the erratic part of your CFT partition function. So in other words, your closed universe actually emerges out of this erratic part of the partition function. Okay, if we live in the closed universe, and then actually we owe our existence to some erratic part of some Lorentzian series. Okay, good. So now let me just collectively denote this M, the Euclidean manifold, and the light operator insertions by this script X. And then you can view this erratic part of the CFT function, CFT partition function, as some kind of functions on this big space. Okay, this is this script X is a huge space. And then the product of those erratic parts then form a commutative algebra, star algebra. You can take the complex conjugate of it. And then this filter then defines a state on this algebra. In particular, the action of this state on the element of the algebra then relates to the wormhole amplitude. Okay, wormhole partition function. Okay. So when you have an algebra, you have a state. When you have a star algebra, you have a state on the algebra. Then that defines a GNS Hilbert space. Okay, so that just this structure itself automatically defines a Hilbert space for you. And so we can call this as a semi-classical Hilbert space for all closed universes, okay, defined by your CFT. And then when you have a Hilbert space, then you have inner product structure, etc. And because of this identification, then that put a non-trivial constraint on the wormhole amplitude. Okay, for example, you can show because of this Hilbert space structure that requires that the wormhole connect M1 to M2, the action is greater than the one connect to M1, M2, M2. Okay, you can derive inequality like this. And actually, infinite tower of such kind of inequalities. Okay, you can so this is something you can principle check explicitly just by working with gravity. For example, the Tom Hartman's talk yesterday may be able to use to check this kind of inequality. Okay, so let me very quickly mention this space-time from internal wormholes. And so a very nice example of such an example is called the Antonini-Sacchetta-Ringo cosmology, which corresponding to two copies of ADS entangled with a baby universe. Okay, so this cosmology is supposed to describe, say, a state obtained by inserting a heavy operator, which is this OR, on the thermal field double state. Okay, so here you imagine this OR is a heavy operator of energy of order n squared. Okay, but now you consider this state below the Hawking-Page temperature. Okay. And below the Hawking-Page temperature, you can roughly write this state as the matrix element of this O in the state, say, of energy of order 1. Okay, so the A and B, again, remember the notations, A and B are the state of energy order 1, corresponding to the state in the, say, in the empty ADS. Okay. So now, if this OAB, this matrix element has a well-defined Lorentzian limit, then this is a well-defined state in the two copies of the Hilbert space of ADSR and ADSL. Then there's no room for the for this baby universe. Okay, as pointed out first by Antonini Ras and developed further by Engelhardt and Gasto. So yeah, so in this case, if this OAB, as I mentioned earlier, this is called the heavy light kind of OPE coefficient. If this has erratic independence, then this can actually be used to generate a new sector, which is the baby universe. Okay, so you can actually describe the baby universe if this has erratic behavior. Okay. And so the fact that this OAB here has erratic independence has actually very important implications. For example, you can look at propagators in the ADS region, which is described by single trace operators, say sandwiched between these states. And because of the state here involving this OAB, which contain erratic independence, okay? So this kind of propagator in the ADS region also contain erratic part, which is order 1, unsuppressed. So that seems to imply, so when you go to the finite n series, when you go to series at n and n plus 1, the quantity corresponding to the ADS propagators can differ by order 1 amount. Okay? So similarly, you can argue that for the propagators in the baby universe. So using the terminology which introduced some time ago with Latta Engelhardt, we can say that this space-time, even the ADS part, is quantum volatile. Okay. Yeah, so there are also many other possible explanations of this square cosmology. For example, can also result from operator averages discussed by various papers. Also, there are some other interpretations, etc. Okay, so finally, let me just very quickly mention the black hole interior. So the same consideration. So again, this so-called the PAT states, you can consider above the Hawking page temperature. Then in that case, then corresponding to long black hole. Okay. So again, yeah, I will not go into detail here. And this state actually is erratic. And outside horizon, you can show that the erratic fluctuations are always suppressed. But inside horizon, they can be unsuppressed of order 1. So the region inside the horizon, again, is quantum volatile. Okay, so let me just conclude by mentioning 3 things. So all this black hole and the closed universe, they all involve singularities. So maybe singularities also have to do with erratic end behavior. And also, how should we understand this quantum volatile behavior, even for the ADS part of the AS square cosmology? Okay, so that's weird, because normally we would think the ADS part would be highly regular. And also what this filter means and implications for the quantum gravity. So I will stop here. Thank you.
Questions? Yeah, thanks for a nice talk. Are you familiar with the unfolding procedure and random matrix theory?
Yeah.
So, right, so it feels very reminiscent. Like, I wonder if you could use that as an explicit filtering procedure, right? Like, we already know that when I take like the Ising model at finite n to actually see chaotic statistics, I need to fit to some polynomial, right?
Yeah, something in spirit. Yeah, just to do it in practice is not easy. Yeah.
Well, in finite systems, people do this explicitly, right?
Yeah,
it's like we know how to actually get, we know that spectral statistics are not in fact self-averaging until you do the unfolding procedure.
Yeah.
So I wonder if I could use, like, if I can use that to actually implement one of your F math.
Yeah, certainly that would be some ideas to try. Yeah.
Can you explain why in the long wormhole pets, the interior could be volatile?
Oh yeah, so the interior can be constructed using this modular flow, and the operator inside in the interior can be constructed in the modular flow. And in this case, the modular flow, the operator essentially is single trace operator, but it dressed in a complicated way by this heavy operator. So this dressed operator is highly erratic. Okay, and so when you plug into this psi O, yeah, it's a generic argument. It's not a proof. Yeah.
Because in the exterior, it also sees this O, but it's not volatile. So
yeah, right. In outside, it's because it's just ordinary single trace operator. And then you can show that when you do the ordinary single trace operator in the high temperature phase, somehow the volatility does not filter into that. Yeah. And only, yeah, not a lot like in this ADS case. Yeah, not like in this ADS case, because you have finite, you have discrete sum here. So the sum in the black hole case is more averaging, so that the outside horizon, you don't have this behavior.
In a space-time that's quantum volatile, do I experience anything abnormal? Do I notice that?
Yeah, I'm not sure. So I want people to think about it. So I would say maybe, yeah, I think this is the question we have to face. Yeah, we have to, yeah. Yeah, let me just emphasize one thing. So the statement I'm making here does not depend on the detail of this filtering. So you can replace this filtering by ensemble average, and then the same thing will happen. Okay, it's really boils down to how we really think about those issues. Yes, please.
I ask this is because you mentioned that this AS square model, even if in ADS region, that part is still quantum volatile, and I assume that's pretty much similar to a completely evaporated black hole. Let's say if I stay outside the black hole when the black hole is completely gone, is the space-time does it might satisfy what you said is quantum volatile?
No, I think that should not be. I think that should not be, but I have not looked at that case carefully. I have not thought about that case carefully, but yeah.
I think they become more similar if you later do some Euclidean evolution on the evaporated black hole radiation. Then you have a few quanta. And
okay.
So you're using this word filtering, but what's wrong with the word coarse graining? I mean, isn't that kind of what we always say about wormholes, you know, going back to the work of Stanford and Shankar?
Yeah. So here's what I emphasize, right? Just say, we are not just changing the word here. We can actually make predictions. You can actually calculate this, right? So you can just say, let's do cross graining. That's a very vague word. So here I try to make that precise in the sense that you can make predictions. I can here you can check whether this proposal is correct or not by calculating some genus 2 partition function, and check the genus 2 partition function whether it has erratic part and whether that erratic part agrees with the wormhole answer. Okay, so there's a content in this rebranding.
I think that was true in the old version also. I mean, the wormhole was predicting some, you know, various...
But this specific independence, right? It's the specific independence. It's not it's not due to uncertainty of average or ensemble.
But there is no ensemble, right? In higher dimensions. No ensemble. So, but coarse graining...
You have to specify what you mean by cross graining, right? Here I give you a precise way what we are cross graining about.
I feel like one of the lessons of Boltzmann is it doesn't matter too much how you put it.
Yeah, I think maybe it doesn't matter to you.
So I think in quantum mechanics, there is a well-defined example of this, which is the Gutzwiller or the Selbert trace formula, where we literally decompose the discrete density of states into some smooth part plus some oscillatory part. And we have an explicit expression for the oscillatory part. And then the filter is, as Daniel was saying, is coarse graining. So the smooth part is what you obtain from coarse graining over some microcanonical window.
Right.
But the nice thing is that you can compute explicitly the oscillatory part.
Yeah.
And then obtain, for example, via Berry's diagonal approximation, you can obtain the wormhole, meaning the linear ramp in the spectrum.
Right. Yeah. That I all agree. The key thing is about what is the origin of this erratic part, right? So here I just try to pinpoint that the erratic part has to do with some kind of erratic dependency in N. Not say you have to do some other kind of ensemble average, say over different series, okay? And just to pinpoint what's the region you have to do this cross graining.
Doesn't this example, which you can do at fixed N, mean that there's no need to do it at large N, the averaging? So in Gutzwiller trace formula, you don't have to do anything about N.
Sorry?
in trace formulas and space.
Yeah.
Still have an erratic part.
Yeah, that's fine. You can have erratic part depend on some other things. Yeah, you can have erratic part depend on some other things. So gravity may have erratic part depend on some other parameters. Here we are talking about G-Newton dependence, right? Here we are trying to resolve the discrepancy in the G-Newton dependence and in the N dependence. That's the key. Okay, we are not doing some random cross-graining. So we're trying to solve that problem. Okay, that's the key here.
Sure. Can you comment on wormholes which have different values of n on each side?
Yeah, I think that's also very interesting. I don't know, have not thought too much about them. So that kind of wormhole which tells you the correlations between the different n series. And yeah, I think the key is somehow to be able to write this kind of formula which you can relate this wormhole amplitude to some precise CFT quantities you can isolate. Okay, so here is just some attempt to do that. Yeah, so I would say try to do something like that also for that case too. Yeah.
Okay, I think in the interest of time, should thank Connor.